and then we will divide it by n. Now let's come to some numerical examples in which we will use matrix maths. In the first numerical, it is required to calculate numeric values of W4 transformation matrix. So in this example, we are not going to analyze any time domain sequence. Similarly, we are not synthesizing any frequency domain sequence. We are just required to find the numeric values of the W4 transformation matrix. Now, in this example, the value of capital N is equal to 4. So it will have 4 rows and 4 columns because the value of both K and N will go from 0 to 3. As you can see here as well. The value of K is updating row wise 0, 1, 2, 3, which is written with a red color. Similarly, the value of small n is updating column wise 0, 1, 2, 3, which is written with a green color. So the W4 matrix will have 16 entries in total, where in each entry the common factor will be W4, which is written with a black color, while the superscript values will be written based on the values of K and N. Now, how we can find the values of this W4 matrix? Mathematically, we know Wn is equal to exponential minus j 2 pi over n. So if the value of n is equal to 4, then W4 will become exponential minus j 2 pi over 4, and the product of K and N will become the power of this factor, and on multiplying those two powers it will be simply equal to exponential minus j 2 pi into 0 over 4. Similarly, you can fill the whole matrix by following the K and N values. Now the next step is we have to find the numeric values of these 16 complex exponentials. If you observe the first row and first column of this matrix, it is very simple to find. The values of first row and the values of first column will be equal to 1. Why is it so? As you are observing, the zero index values in the first row and first column. The values of first row will be equal to 1 due to K is equal to 0 in all of these 4 entries. Since the first row of W matrix is going to be utilized for the calculation of DC harmonic, that's why the K index is 0 in all these 4 entries. So due to K is equal to 0, the first row of this matrix will be equal to 1, and why the first column of this W4 matrix will be equal to 1? The reason is small n is equal to 0 in the first column, and n is equal to 0 means the first index value of the small n vector. So due to n is equal to 0, the first column will be equal to 1. So no matter what is the value of n, the values of first row and first column will always be equal to 1. If the value of capital N is equal to 1024, then it will be a matrix containing 1024 rows and 1024 columns, but all the values of first row and first column will be equal to 1 due to K is equal to 0 and due to N is equal to 0. Now we are just left with these 9 complex exponentials whose numeric values can be found very easily. So let's see what are the values of these complex exponentials. So these are the 16 numeric values of a W4 transformation matrix, which is also called a matrix of linear transformation. And as you can see in this numerical, we have just found the values of a transformation matrix. We have not calculated the spectrum of any time domain sequence. Similarly, we have not synthesized any frequency domain sequence. We have just calculated the values of this transformation matrix. And the point to remember is that the values of this W4 matrix will always be equal to these values, no matter what will be the actual values of our time domain sequence or what will be the values of our frequency domain sequence. whenever it will be required to calculate 4-point DFT or 4-point inverse DFT, we will need to use the W4 matrix. So the values of this W4 matrix must be pre-calculated or pre-stored on our computer memory in order to save computational time. So the idea is the values of W4 matrix or the values of any Wn matrix must be pre-calculated. So we will just acquire our signal and we will multiply the time domain signal with the W matrix in order to get the spectrum. So in this particular way, we can save computational time because these values will neither depend on a time domain sequence nor these values will depend on the frequency domain vector. Another important observation about this W4 matrix is if you observe the values of this W4 matrix closely, then you will find only 4 unique values in this matrix, which are 1, -1, -j, and +j. So in this W4 matrix, there are only 4 unique elements, 1, -j, -1, and +j, while the remaining 12 entries are the redundant versions of these 4 unique values, which can be calculated using periodicity and symmetry property of the DFT as well. And this idea of calculating transformation factor values will be covered in the later slides. So the conclusion is for an n-point DFT, we will have a transformation matrix of nth order which will have n rows and n columns. But in that particular matrix, we will have only n number of unique elements. So let's assume if the value of n is equal to 16, so the transformation matrix will have 16 rows and 16 columns, but in that complete matrix you will just find 16 unique elements. All the remaining elements will be the redundant versions of those 16 unique values. And this is the reason why DFT is computationally slow. And in the upcoming lectures we will discuss FFT, which will eliminate this redundancy in order to calculate Fourier transform efficiently in real time. Now let's observe another possible method to find the numeric values of W4 transform matrix. Basically it is not a new method, we are just going to simplify the values of k and n which are written in the superscript of W4 notation. So instead of keeping both k and n individually, we can just simplify these numbers by multiplying these two superscript values. So 0 into 0 is simply 0, 0 into 1 is 0. So you will find 0 in the superscript of both first row and first column. Similarly, 1 into 1 will become 1, 1 into 2 is 2, 1 into 3 is 3, 2 is to 1 is 2, 2 into 2 is 4, 2 into 3 is 6, 3 into 1 is 3, 3 into 2 is 6, 3 into 3 is 9. So you will have the W4 matrix where you will find only one number which is written in the superscript of W4 factor. Now we can simply calculate the values of this W4 matrix by replacing W4 by exponential minus j 2 pi over 4, where the superscript value will become the exponent of those complex exponentials. So this is how we can write a W4 matrix in the form of complex exponentials, where the first row and first column will be again 1. Now let's calculate the values of these 9 complex exponentials. Let's start with this value. So 4 and 4 will be cancelled each other. So exponential minus j 2 pi will be equal to 1. So the value of this factor will be equal to 1. Now let's come to these two values. So 2 into 2 is 4, 4 over 4 is 1. So exponential minus j pi will be equal to minus 1. So the values of this factor and this factor will be equal to minus 1. Now let's come to these two values. Exponential minus j 2 pi 6 over 4. So it will become exponential minus j 3 pi, and it will also be equal to exponential minus j 3 pi. and exponential minus j 3 pi will also be equal to minus 1. So the values of these two factors and the values of these two factors will be equal to minus 1, while the value of this factor was 1. Now let's come to this value and this value. Exponential minus j 2 pi over 4, so it is basically exponential minus j pi by 2, and exponential minus j pi by 2 is basically minus j. Similarly, exponential minus j 2 pi into 9 over 4 is basically exponential minus j 9 pi by 2, which is also equal to minus j. Now let's come to the last two values, which is this one and this one, which are both same. Exponential minus j 2 pi into 3 divided by 4. So basically it is exponential minus j 3 pi by 2, and exponential minus j 3 pi by 2 will be equal to plus j. So the values of this factor and this factor will be plus j. So we have got the same values of W4 matrix as we obtained previously. Now let's come to the second numerical, in which it is required to calculate 4-point DFT of the given discrete time sequence, whose values are 1100 by